Greetings of the day. So welcome back to our lecture series on the course Material Science and Metallurgy. So today's topic is defects in solids. The overview of today's presentation includes the basic introduction to the defects in the solids. Then we will look at a case study that is a classic failure from the materials perspective. That is a Titanic ship's failure, the Titanic steel failure, a case study on the material defects. Then we will classify the defects based on the dimensionality, so that is point defects, line defects, surface defects, and volume defects, and we will summarize at the end of our today's lecture. So crystalline solids are expected to have a perfect atomic arrangement. That is in theory, but in reality or in practical scenario, all solids contain defects, certain defects. So these defects can influence almost all the properties, that includes mechanical, electrical, thermal, and other properties, optical and other properties of the material. So it is very much needed for understanding with a clear picture on the defects that are present in the materials. So we will look at a case study, why we have to understand about the materials defects, which is very important for the materials scientists. So we have here a tragic sinking of RMS Titanic that has happened in the 1912, which is one of the history's most infamous disasters. So we know that the Titanic ship is hit with the iceberg. Basically that was a trigger, but it was indeed failed because of the ship's materials defects that played a crucial role in the failure. So we have the ship here, and the classic 3D scan image that is been provided here. So this is a 3D scan image developed from out of 15,000 or nearly more than 15,000 images together joined and created this particular 3D scan image. So where when one can see the material, the Titanic ship that has a wreck in the hull region that is looked at peripheral level outside on the contrary, and we have the stern part and the bow part, both are separating the middle portion, right? So we look at this case study and understand the significance of materials defects. So if you look at the major key points, so this is a Titanic ship that is struck an iceberg on April 14th precisely in the year 1912. So during those years, this ship was built with the promise that it is a ship which nothing can happen to this ship. That is a kind of wording was there, buzz was there during that time. But unfortunately, in its first voyage itself, this Titanic ship has sunk into the sea. The hull is cracked open, and the ship sank within 2 hours 40 minutes, and that is something which is a catastrophic phenomenon, catastrophic failure of that particular big ship. So almost like 1,500 lives have lost. But why did the ship fail so quickly? It is 2.5 hours, but why did the ship failed so quickly? In its first voyage itself, the ship was being sank into the sea. When the Titanic sank, the hull broke into two parts, as in the movie also we have seen. The Titanic hull, the hull portion has broke into two parts, basically, which is basically a brittle manner. It is not like a ductile failure. It is a brittle failure, a sudden failure. But in steels, usually steel is known for it is basically a ductile material, right? Steel is a ductile material. It is not like a brittle material like ceramic or other brittle materials, right? So this is a ductile material. This Titanic is made out of this steel, but instead of having a ductile failure, but the Titanic ship has seen a brittle failure. So what is the reason behind it, right? So we will look into it. We will closely look at the materials, its properties, that is the materials that have been considered, and what is the root cause for the failure of these Titanic ship. The key material defects that are being observed after systematic investigation has been happened in the metallurgical perspective as well as the scientific perspective also. It has been identified that the brittle steel, the steel that is being used, which is noted with some point defects that are present in the material. So something like in its composition, it is observed with high amount of sulfur and high amount of phosphorus that made the steel brittle, especially at the very low temperatures. The Atlantic Ocean, its ocean temperature is close to -2 degrees centigrade. So that has worsened the properties of the overall steel. So it has promoted the brittleness in the material, and when a material is subjected to brittle in nature, so if a sudden load is acted on the material, so it will behave in a brittle manner. It will fail in a brittle manner. So that caused the hull, when it hit with the iceberg, so that caused the hull to crack instead of deforming. Deforming is being noticed in the ductile materials, but instead of exhibiting a ductile behavior, deformation behavior in the steel, but it was due to the high presence of sulfur and phosphorus in the steel composition, so which led to its brittleness. This is one of the materials defect that has been identified in the material perspective. And in the joining operation, usually those times riveting has been widely accepted during those days. So the rivets are being manufactured out of iron, and which is found with impurities, and that cause the structural defects in the material. So rivets has been identified with rivets are made out of iron, and iron rivets are being contained. It is observed to be contained with very high amount of slag. So that is which is prone for the fracture under especially lower temperatures, sub-zero temperatures. These rivets are popped out under the stress when the ship has been hit with such a sudden impact. So these rivets are popped out under the stress, and which caused the plates to get separated in the ship, and which caused the catastrophic failure of the Titanic ship. So these are the one due to the joining failure, and also one due to the material selection, the selection of right composition for the steel that has played a crucial role in the material perspective, and which is identified in this particular case, is found with the defects, and which caused the catastrophic failure of the Titanic ship, right? So it is so all the solid materials which basically contains defects. So sometimes these defects are intentionally added, and some are unintentionally it has been identified in the material. So if you take an intentional addition of these defects, could be that process could be called as a dopant, where impurities have been added to the material. For example, if you look at the silicon is being added with the dopants in order to improve the performance of the silicon, which is being used in the most of the semiconductor materials, what we are seeing in our mobile phones and the computer chips and all. Right, that is an intentional addition of impurities into the material. That is actually we can call it as a defect, which is any material which is having instead of having a regular atom in the systematic arrangement, if any deviation is being identified in the material structure, and that we can call it as a defect in the material. Right, so all the materials contains the defects. It could be an intentional addition, or it could be an unintentional. It has been present or identified in the material. These defects will influence the strength properties. So something like it can influence the strength and its behavior, whether it is ductile or the brittle, and its conductivity, and also the durability, the lifetime of the material. So defects will have a significant role in the properties of the material here. So engineering materials have been designed by controlling these defects. So whatever engineering materials we are seeing right now, we are witnessing these days, they are being controlled. These defects are being well controlled for delivering the better performances, right? The Titanic's failure shows why defect analysis is clear. So it is very important that we have to clearly understand about the defects and what are the types of the defects and what could defects that are present at different stages, microscopic level and as well as the macroscopic level. So we have to understand the defects and how we can control it, not just by understanding it. Later we have to control it. How do we control it, and so that we can improve it, improve the performances, not the defects. By controlling the defects, we wanted to improve the performance of the materials. So if you look at the classification of defects in the solid, so based on the dimensionality, the defects have been categorized into 4 categories. So first one is a point defects, which is a 0-dimensional defects. We can also call it as a 0-dimensional defects. Then we have the defects in the 1-dimensional, so defects that has been observed along a particular line, and in the point defects means defects that are being identified at the atomic level. So if any defect is observed at the atom level for that particular material, those defects we can call it as 0-dimensional defects or point defects in this case. Then line defects, defects that are being identified along a particular line. So along a particular line, if you see the misalignment of the atoms in its structure, and those defects we can call it as a line defects. Then at the surface defects as it is a 2-dimensional defect. In both the directions, the deviation in the atomic arrangement can be noticed, so that is a 2-dimensional defect. And at the volume level, so all 3 dimensions, so x, y and z directions, if you observe the defects, the misalignment or the misarrangement of atoms has been noticed. So those defects we can call it as a volume defects. So in the point defects, we can see the missing or misplaced atoms could be the defects that we notice. In the case of line defects, misaligned row of atoms along a particular length or along a particular direction, along a particular alignment. So if you notice the disturbances in the atomic arrangement, then we can call it as line defects. Then irregularities have been observed at the boundaries. These boundaries are mostly the 2-dimensional directions. This could be a grain boundaries. There are the surface defects. And large scale voids are the cracks that has been observed. What we practically see it, these voids, like porosity in the casting process, we observe the materials having the porous nature. So those voids, large scale voids, those can be the volume defects, which occupies basically in all 3 directions. And cracks and certain inclusions of the foreign materials that has been accommodating into the material. So we look at it briefly about all these defects. So we'll start with the point defects. So point defects further been classified into many defects. So one of the defect is under the point defects, that is a vacancies. Vacancy is nothing but it is in the regular arrangement of the atom. If we identify any missing atom, so that is called as a vacancy, something which is empty in that particular area. Atom need to be present, but if the atom is being missing at that position, that is considered as a vacancy. So that is a vacancy defect that happens at the atomic level, and so it is a point defect. So if we from this image, if you closely look at, you see here the second defect. So this is the regular arrangement of atom, but in this case, you see the 2 here, one atom is missing. So that is basically vacancy here. Then interstitial defects. Interstitial means in the regular arrangement of an atom, so in between the regular arrangement atom, if we see any an extra atom is being situated, that is called as the interstitial defects. So extra atom disrupts the structure. So if you look at closely, this is a one interstitial and this is also another interstitial. You see the regular arrangement of atoms that you can notice is orange colored atoms. So the white colored atom is there, one, that is a foreign atom that has been occupied the interstitial site of the crystal, right? This is called as a interstitial atom. So this is basically the same from the same group of atoms. So one of the atom is been occupying the interstitial sites, that is called as a self-interstitial defect, right? Then we have the substitutional defect. Substitutional means, as we see in the cricket matches also, one player has been substituting in the place of another. Similarly, in the material perspective also, one atom is been substituting in the place of another atom. So where you can see this defect in the regular arrangement of atoms. So in this case, in the place of orange colored atom, so there is a white colored atom is been situating. So in the place of that, one is been substituting. So such kind of defects are called substitutional defects. So different atoms replace the original ones. That is a substitutional defects. So in the case of titanic steel, so titanic steel is having the high sulfur content, that is being that could be a substitutional defect, or it might be occupying the interstitial defect. Basically, it is happening at the atomic level. So which caused high amount of the sulfur, which acted as an impurity that reduced the overall toughness of the material, overall toughness of the steel. Sulfur has reduced the overall, high amount of sulfur has reduced the toughness of the material, right? So there are other defects also you can closely look at, which are all these defects you can see, those are basically you can notice at the atomic level. So all these defects we can call it as a point defects. Atomic level, the defects that are observed at the atom level or the single atom level or a group of atoms, so those defects we can call it as a point defects. These are vacancies, interstitial and substitutional defect. Then we have the line defects. So line defects are of two types. One is edge dislocation and another one is called screw dislocation. Dislocation means something which has been not located in its original position, but it has been dislocated. Atoms have been dislocated to the new positions. If it has been observed with a group of atoms, then that is called as a dislocation. The atoms have been, instead of situating its original position, it has been relocated. So dislocated. So line defects are also called as a dislocation. So these dislocations are of two types. One is edge dislocation and another one is a screw dislocation. When the edge dislocation has been caused, when an extra half plane of atoms are being present in the structure of the crystal, so that could be the edge dislocation. So practically also, if you look at the cone, so there are regular arrangement of line of these cones, and an extra plane of cone is also been observed. Extra layer has been observed from the regular arrangements, right? This extra plane of atom, so that is basically causes the extra half plane of atom, that is basically causes the edge dislocation. Okay, this is a extra plane of atoms that is coming here. Okay, so if you closely observe it here, yeah, so this is an extra plane of atoms that has been present here. So right, this is an extra plane of atoms, right? So in our steel, these steels can be strengthened from these dislocations by strengthening mechanism. One of the strengthening mechanisms that helps in regulating this dislocation density or improving the strength could be the work hardening technique. This is a cold working process. We will look at it in our upcoming classes. What are the strengthening mechanisms? So steels will be strengthened basically from the work hardening technique, which increases the dislocation density, and in turn it improves the strength of the material. So titanic steel lacked ductility, so it couldn't absorb the impact strength. So this titanic steel, which lacked the ductility and absorbed the brittle behavior, and that is a cause behind its failure. So as it is lacked the ductility, it cannot absorb the impact strength that has been caused by the iceberg. Then the other defects are surface and volume defects. Surface and volume defects, basically it creates a structural weakness. So the types of these surface defects and the volume defects could be surface defects under that category, the two-dimensional defect. So one is grain boundaries. So grain boundaries are the misalignment of atomic arrangement, especially in the polycrystalline material. In the polycrystalline material in the previous class we have seen, so there will be multiple grains that have been situated. If this is a polycrystalline material, this is a grain 1 and this is a grain 2, 3 and 4. So between the two grains you will be having the grain boundary. So in this particular grain boundary region, atoms will not arrange in the regular position. It will not consider the grain 1's regular arrangement. It will not consider the grain 2's regular arrangement. But it will be in this grain boundary region, it will be in its own arrangement. So it is basically deviated from either the grain 1 or grain 2. It won't be having any of these grains arrangement. So that is a again defect, because there is no regular or systematic arrangement. If the systematic arrangement is there, it's crystalline behavior could be there, right? So that is a misalignment of atomic structure, and this happens at the two-dimensional level, and so it is one of the example for surface defects. Okay. Then we have these voids and cracks. Voids and cracks are the bulk porosity that has been observed in the casting process, in the casted products. Okay. These are large scale defects that we can observe it from our naked eyes. Okay, with our eyes we can able to see those cracks or the voids. These are basically bulk defects, are also called as a volume defects. So these large defects causes the premature failure of the material. Okay, inclusions can be any foreign particles that you can embed it into the metals. Any foreign particles, if you embed into the metals, and that is also a classic case of volume defect. At the volume level, we are incorporating the foreign materials into the metal, and that is also causes a volume level defects. So these are the examples for these are the volume and surface defects. Okay. In the case of our Titanic example, so rivets are having riveting joints. Riveted the component, the plates have been joined by the riveting process. So rivets are basically iron rivets have been used for joining. Iron rivets have been used for joining the sheets here. These iron rivets are having, it is observed to have high slag content. That is an impurity. Okay, at the volume level impurity that has been observed. So which causes the forming the weak inclusions that cause the fracture, which eventually cause the fracture. Fractures in hull plates that led to the rapid water entry. So when it has been hit and then the material has been failed, and also when it is hit, the two plates that have been easily separated because of the weak rivets, okay, and rapidly the water has entered into the ship, and eventually that caused a lot of stress and the failure of the Titanic ship. So in the nowadays, the shipping materials are being maintained with high strength as well as the purity, good purity, and the composition has been carefully selected for the materials, and by taking care of all these parameters, all these measures, we are ensuring the safety of the overall vessel. Right. So what are the strategies that we consider for defect control? Now we have seen different defects: point, line, surface and volume defects. So what are the strategies? How do we prevent those kind of catastrophic failures that has been observed? How do we prevent it? So what are the strategies for this defect control? So first thing is we have to carefully select the materials for the building these kind of ships. Even the alloy composition has to be carefully selected. We have to have a clear understanding of each and every material's inclusion. Use the alloys in the controlled composition. So we should have the exact proportion, how much we have to consider. So that has to be clearly understood. And its behavior under different conditions, sub-zero temperatures and higher temperatures, are the normal temperatures that need to be clearly understood. How its behavior, whether it is ductile or brittle under sub-zero temperatures, that has to be clearly understood. So the right selection of the material is one of the key strategy that is to be applied to control the defect. And then by doing the heat treatment process, we can reduce the brittleness of the material. So one such heat treatment process could be annealing process. By doing this annealing process, the atoms will relieve its stresses, internal stresses that has been caused during the manufacturing of the component, and atoms will relax into its positions, and that is basically improves or reduces the overall brittleness and improves the ductility of the material. So by doing the proper heat treatment process to the material, one can control the defect. Then after these careful steps, so one has to check the quality of the material. So using now a lot of quality testing tools have been available right now in the 21st century. So these includes the X-ray inspection or the ultrasonic inspection that basically observes the cracks that have been, even the micro cracks that have been observed in the material. So quality checks are the measures that we have to consider to control the defects in the material. And finally, the design modifications have to be carefully considered. The design modifications, which include replacing the traditional way of joining methods using the advanced welding techniques instead of going with the riveted joining operations, right? So by carefully selecting these strategies, one can control the defects in the material. And the Titanic's disaster that taught the engineers the importance of material science. In basically this catastrophic failure, we have to learn from the what has been happened. We cannot change it, what has been happened. So we have to learn from our experiences, from our failures. So engineers have taught the lesson and understood the importance of material science, the selection of right material for the engineering application. And today's ships are accommodated with the better materials, and they are being welded instead of riveted joints, and they have been advanced. They have been tested advanced testing strategies, advanced testing tools are being used to prevent any such kind of failures. Right, all these steps have been carefully taken in today's engineering applications. So in summary, so the key takeaways that will be from this lecture could be, so materials defects can determine the success or failure of structure. We have discussed this with the classic example of Titanic ship. So Titanic steel, so we have also seen the root cause of the failure of Titanic ship. So that in the materials defects point of view, so mainly we have discussed the Titanic steel, which is composed with high sulfur and phosphorus content, which cause the brittle behavior to the steel, especially at the sub-zero temperatures or the -2 degrees cold water in the Atlantic Ocean. And the riveted joints, the iron rivets that has been failed because of the impurity, the slag contents, high amount of slag content, that's also reduce the strength of the riveted joint, and which cause the failure of the Titanic ship. These are the inherent material defects that are being noted on the Titanic ship, which cause its failure, that we have discussed in today's lecture. So based on these understandings, so engineers must study about these defects and should understand the controlling, should develop the controlling strategies and utilize the defects wisely. So that's what we have seen. So these defects could be unintentionally added for our better performances, like the dopants what is being doing in the silicon for improving the performances. Like that, we have to utilize the defects in the wisely, carefully. We have to control it. So that will happen only by understanding it. Modern material science has dramatically improved safety and durability. So our current modern material science has dramatically, significantly improved with the advanced, lightweight, stronger materials, and that in turn it improved the safety and the durability of the material also. It can last for the certain time also, right? So these are the key takeaways from today's lecture. I have taken certain images from the certain links that I have posted already, and this could be one of the links which discusses briefly about the defects in the solids. One can go through it, and also textbook references throughout our course. The textbook references that I can recommend is a Callister's textbook, that is a Material Science and Engineering and Introduction. Right. So these are the references that I have used. So thank you for today's lecture, and we will meet in the next lecture with a detailed focus on point defects. What are the different defects that are being we will discuss in detail about the vacancies and different impurities that have been there, and also we can discuss the other defects also. Right. Thank you very much.